Good morning, Year 13. Very well done in the work you did on calculating delta S. It looks like that went pretty well, and you've got the hang of it. Right, so we're going to go up a notch in terms of difficulty, I think, today, and I'll do my best to explain this as clearly as I can. It's one of these things. It's probably, again, easier to do in front of you, but I'll do my best, and I'll stick around online if you want to talk to me during the course of the lesson. Right, okay, so we have spent time learning how to calculate delta S. Change, or sorry, the change in entropy, or the delta S for a particular reaction. Now, if we're to give that its proper name, that's what we call the entropy change of the system, okay, which is delta S system here, as written in this equation. But for any reaction to be spontaneous, we need to consider not only the entropy of the system, but also the entropy of the surroundings to give the overall entropy change, sometimes called delta S total, of the total entropy change, or sometimes, for example, in your textbook, it's given as delta S of the universe. Okay, so in other words, the overall entropy change for a reaction is dependent on the entropy change from within the system and the entropy of the surroundings. Okay, now you know how to calculate entropy of the system. That's what you were doing last lesson. But to the entropy change of the surroundings, delta S surroundings, is all going to be explained today. Okay, so that's all going to come together today. But for now, what I want to make clear is, for a reaction to be spontaneous, it's this number here, this total, delta S total, which has to overall be positive. So delta S is positive, means there's a positive entropy change overall. It means the reaction is feasible. It can happen. It will be spontaneous in a chemistry sense. What spontaneous means in a chemistry sense is it's thermodynamically feasible. It can happen. And if the overall entropy change, delta S total, or delta S of the universe, is negative, so less than zero, the reaction is non-spontaneous, not feasible, can't happen. I'll come back to this, but sometimes, as I've said, I think before in previous lessons, reactions can be thermodynamically feasible, and sometimes called spontaneous, but it might be that they're kinetically stable. In other words, you need to overcome an activation energy barrier. Okay, but don't worry about that just for now. We're looking at calculating the entropy change of the system, which we learn how to do. We'll then combine it with the entropy of surroundings, and we'll combine it into we'll work out the overall entropy. If that's positive, then the reaction can go. But the good news is we don't have to do this sum. We just need to be aware of what I've just said. Okay. This equation, and I'm not going to do the derivation because you don't need to know how to do it, can be converted to a different equation, which is one where instead of using delta S total or delta S universe, we start to use delta G. And you've heard us talk about delta G before. We've been looking at other topics. Okay. All right. So here's a kind of definition for you, but this is the Gibbs free energy, which relates the energy that can be obtained from a chemical reaction, and it relates it to the enthalpy change, which, by the way, relates to the entropy of the surroundings, delta S surroundings I was just talking about, and delta S of the system, which is what you learned to calculate before, and absolute temperature, which is measured in Kelvin. So this is the equation that you're going to have to learn to use, which really is just a derivation of what I was just talking about up over here. Okay, so you need to be aware of this. This is a confusing equation because you've got lots of S's, systems, surrounding, and total, whereas this is the one that you're going to use and be comfortable using in your exam. Okay, so make a note of that now, please. You might want to make a note now that delta G is in kilojoules per mole. Delta H is in kilojoules per mole. We measure delta S typically in joules per mole per Kelvin, but if we use it in this equation, we're going to have to use it in kilojoules per mole per Kelvin to make it match up with these other numbers we're using over here. And obviously temperature is measured in Kelvin. So that equation must be pinned to your eyelids, ready for any exams that might come up on this. Okay, so Gibbs free energy. Right, and there it is again over the page. As I've said already, these are the units. I'll come back to what it says up here in a sec. The units are kilojoules per mole, and we need to know now that if delta, and we've mentioned this before by the way, so this isn't going to be completely new to you. If delta G is negative, then the reaction is spontaneous, i.e. can proceed. So thermodynamically feasible is another way of putting it. And if it's delta G is positive, then the reaction is non-spontaneous, it cannot proceed, not thermodynamically feasible reaction. Okay. And don't forget, the word spontaneous doesn't mean the same as in normal English. Spontaneous means it just can happen, provided it can overcome the activation energy barrier that might be there. Right, so how to use this equation? Usually what we need to do is to work out what delta G is. We know how to work out delta S because you've done that last lesson. We have to convert that to kilojoules per mole by dividing by 1000, multiply by the temperature in Kelvin. But we need to know how to calculate delta H. Now the good news is we already know how to do that as well, because we learnt it last year. We used Hess cycles and things like that to work out delta H last year, so that should all be nice and familiar. It's just a case of piecing it all together. So, share with you a couple of pages from your IB textbook that you got. This is the big fat textbook that you got given at the start of last year, and I'm going to walk you through examples from that, which are past paper questions. But I'm just going to show you something before I do that. So the ways of calculating delta H, there are a number. Okay. The first way one might do it is using bond enthalpies. So depending on what the question is, it will always be really clear to you what you have to do. It might be that you have to calculate the enthalpies of the bond broken, take away the enthalpies of the bond formed. You've done this right from year 9 and certainly year 10, where you've calculated the theoretical enthalpy change based on energy changes of bonds broken and bonds formed. You know how to do that. I'm not going to spend any time on that right now. More likely, again, this is a skill we learnt last year, you'd have to use this equation using the enthalpies of formation of the products and the reactants. So if you add together, so it's something we learnt last year, if we add together the enthalpies of formation of all of the products and multiplying by the coefficients each time, if there are, say for example, 3 water molecules produced, you'd have to multiply the enthalpy of formation of water by 3. And then you take away the sum of the enthalpy change of formation of all of the reactants. Okay, so that's probably the most likely one you'd have to use, but not necessarily. It might be. This is certainly something I've seen in exam papers where you'd have to calculate delta G, you'd have to calculate delta H from experimental data using Q equals MC delta T, then calculating delta H by doing minus Q over N if it's an exothermic reaction, or just Q over N if it's endothermic. Or it might be that you're doing enthalpies of combustion, in which case it's just the reverse of what's over here. So this is kind of from a Hess cycle, but the shorthand way of doing it is working out the enthalpy changes, the sum of the enthalpy changes of combustion of the reactants, take away the sum of the enthalpy changes of combustion of the products. Now you'd use, so Hess's law would take you to these two ways of doing it, the second way and the fourth way, but nevertheless you need to know how to calculate delta H, and you've done plenty of practice of that. So let's look at the textbook examples. Instead of the textbook example I was going to show you, I have worked that out and I will show you that in a bit, but it's quite a difficult example, so I thought I'd do this one first, which is a kind of more likely thing you're going to get, and probably a little bit easier as well. So we'll do this one to start with. So here's a reaction where you've got zinc carbonate being thermally decomposed into zinc oxide and carbon dioxide, and you're given in the question delta H is the formation of the product, the reactant, and both the products, and you're given the entropies, standard entropies of the product and the reactant. So we can calculate delta H, delta S, and delta G for these without too much difficulty, hopefully. So to start with, I've already mentioned we know how to work out delta H if we know the delta H's of formation, and they're given to us in this question. So delta H is equal to the sum of the enthalpy changes of formation, the products, take away the sum of the enthalpy changes of formation of the reactant. You should be pretty comfortable with that equation. It does come from Hess's law, but it works, and you need to know that one really. That's going to come up at some point or other, I'd have thought. So we can just pop those numbers into this equation, and we've got zinc oxide, which is minus 348. Add carbon dioxide, which is minus 394. Just pop those in brackets. We've got take away the enthalpy change of formation of the reactant, which is minus 812. And I make what's in that bracket there minus 742, and then we've got to add to it 812, which comes to 70 kilojoules per mole. I don't want to see anyone writing numbers without writing what the units are with them. So that's how to calculate delta H for that reaction. Don't forget, if you're using this method for calculating delta H, if there were 2 lots of zinc oxide and 3 lots of carbon dioxide formed, you'd have to multiply those numbers up. Don't forget. But you've all got the hang of that. So you know how to calculate delta S because you did that the other day. So let's calculate delta S now. So delta S over the system, this is the sum of the standard entropies of the products, again, just like you did before, which is 214 for carbon dioxide and 44 for zinc oxide. Take away the sum of the entropy of the reactants, which is just 83, isn't it? Just write 83 there. I don't really need those, do I? I don't know why I've written those in there. And 214 add 44 is 258 minus 83. 258 minus 83 comes to 175. And so that's an increase in entropy, isn't it? And that's what I'd expect. So I always just have a little check to see, is the entropy change what I'd expect it to be? We've started with a solid, we've ended up with a solid and a gas, so we'd expect the entropy to increase. It's really important you remember to write the units again, which in this case are joules per mole per Kelvin. Now we must remember to convert this to kilojoules per mole when combining it in the delta G equation. So let's divide that by 1000, which is 0.175 kilojoules per mole per Kelvin. And you have to write the units, folks, otherwise people won't know what you're doing. The equation you need to learn, memorize, be comfortable with. Delta G equals delta H minus T times delta S. So this is all part A still, by the way. We're just calculating delta H. We've done that. We're now calculating delta G. Delta H is equal to 70. Take away the temperature, which is in this case 298 times 0.175, and that comes to, sorry, I just realised you gone off the screen there, and I wanted to just tap into the calculator. So it's 70 take away 52.15, 70 take away 52.15, that comes to 17.85. The units for delta G are kilojoules per mole, and that's our answer for delta G. Okay, I'm going to check these in a minute. Hopefully I've got them right. Right, so then we have to answer this really standard, really common question: is this reaction feasible at 298 Kelvin? Now, if delta G is positive, which it is here, then no. Let's say no as delta G is positive, and it's only spontaneous or feasible if delta G is negative. Question C then, I've not mentioned this yet, but this is a pretty standard follow-up question to all of these delta G questions, which is at what temperature range will, or in this case, it gives the temperature range in which the decomposition of this reaction is feasible. Now we're going to come back and talk about some of this stuff in a minute, but I'm just going to cover this right away. So let's bring this back so I can see it. So you've got this, hopefully you've printed this out so you can see it, but give the temperature range in which the decomposition of zinc carbonate is feasible. It's not feasible at 298 K, so what temperature is it feasible? Now the way to solve this puzzle is we use this equation that we've been using and we're going to become familiar with. And the point at which a reaction becomes feasible is the point at which delta G goes from being positive to negative, and that is when delta G is 0. So we set delta G to equal 0 is equal to delta H, which we know. I'm just going to write delta H minus T delta S. And then if we fiddle around with this a little bit, we bring the minus T delta S over to the other side. So T delta S is equal to delta H. It's just a rearrangement of that, setting delta G to 0. We know delta H is what we just worked out, which is 70. We know delta H, sorry, that was delta H, delta S is 52.15. T times 52. Oh, you muppet green. Cross that out. Tell I'm doing it live, can't you? That's 70. T times, where's delta S? It's up here, look, there we are, 0.175. I knew I'd make a mistake, should have done it in advance. And so we can rearrange this to make T the subject to the equation. T is equal to 70 divided by 0.175. What does that come to? 70 divided by 0.175. And that's 400 Kelvin. So that's the temperature at which delta G goes from being positive to negative. We know that at temperatures below that, for example 298, the reaction is not feasible, but at temperatures higher than that, it is feasible. So the greater the temperature, if we look back at this equation here, the greater the temperature, the greater this number here, the more likely it is, if you like, that this number is going to be bigger than 70, if that makes sense. So make this number 400, this overcomes the 70 that's here. So 70 minus a number that's greater than 70 is 0. So in other words, temperatures greater than, so leave it at 400, so delta G is negative at temperatures greater than 400 Kelvin. In the question it says what temperature range is the decomposition of zinc carbonate feasible. So you can't just say at 400, you must say 400 and above. The reaction becomes feasible. Alright, so that's how to tackle questions like that one. So hopefully you've worked through that with me. And I'm delighted to say that I didn't, I've just checked the answer here, and you've got this in your answer pack, which I'll send you, but I got that right. It's exactly right. That's how you go about it. So we're going to move on now. Lots more I want to tell you, lots more I want to talk about, but actually I think I'm going to stop now. I've been talking 20 minutes. That's probably enough for anybody. It's enough for me anyway. What I'd like you to do is you're going to look at page 26 on the pack now, which I'll share with you. Right, so I did mention looking at one from the big textbook. I'll come back to that in another lesson. But we need to look at page 26 now. And there's some questions on here I'd like you to do. So there's 5 questions, like the one I've just done. So question 1 is really easy because it gives you delta H, it gives you delta S. You've just got to plug this into the delta G equation. Not forgetting to convert the delta S into kilojoules per Kelvin per mole and answer the questions here. I'd like you to do question 2, 3, 4 and 5, all of which you're going to have to work out delta H and work out delta S, then combine them in the delta G equation. So delta G equals delta H minus T delta S. Do that for those questions, please. Don't worry about the questions below. We're not going to worry about those just for now. So questions 1 to 5, I reckon that'll do you for the day. I'm going to stick around in the lesson if you need me. So come and grab me if you want some help.